Hello, everybody. Today I will be solving problem 2.17 from Griffith's E&M book, 4th edition. So the problem states an infinite plane slab of thickness 2D carries a uniform volume charge density rho. We're going to find the electric field as a function of y, where y equals 0 at the center. Finally, we're going to plot the electric field versus y. And so to proceed, we will be using Gauss's law. And Gauss's law states that we have a closed surface integral of the electric field dotted by some infinitesimally small distance dA equals a charged enclosed, so Q enclosed, over epsilon naught. And so we will be using a Gaussian pillbox inside this slab to proceed. To better illustrate this, we will be looking at the slab from the front view where this red box is highlighting. And so here is the different view. Here we have the ZY plane with the X plane pointing towards us. So to note, the slab is from -d to d, which is the width of the slab 2d. And for the pillbox, we go from 0 to some distance y here, and again 0 to some distance -y. So overall, the length of the pillbox is 2y. And so we note that the length of the pillbox is less than the width of the slab. So we are in the case where y is less than d. So we can view this problem as initially one infinite plane in the xz plane. So this is the plane, not a line, but we're looking at it from its side. And we have some pillbox here. And if we were to draw some electric field vectors, so we have one going here, and let's say we find another one going in this direction, we note the xz components cancel out, but the y direction exists still, so the electric field will be pointing in the y hat direction for this infinite plane. And we can view the infinite slab as many of these planes added together, and due to the superposition principle, the electric field will still point in the y hat direction. So for the slab, the electric field will point in the y hat direction. We also note that due to the rho being a uniformly distributed charge within the slab, at the origin, if we're looking to the left or to the right, the strength of the electric field will remain the same because the charge will be distributed equally on the left and right-hand side. And we wanted to note that for the electric field component, now the y hat direction. And so we can view the electric field as E equals E y hat, since there's only a y hat component to our electric field. And so focusing on Gauss's law, we have this surface integral of the electric field times dA. And so we have three different surfaces for this Gaussian pillbox. These two faces right here, and our curved surface here. And so we note the electric field points in this direction here, the y hat. Our electric field will point in the negative y hat direction. We can also write it as this y and then y hat. And again, on this curved surface, it'll still point in the y hat direction. And so our differential areas, though, will be pointing here for this curved surface dA up, and then it'll follow dA and dA. And so we see here that when we do the dot product, we can separate this integral into 3 different integrals for each surface. So when we do the dot product, only these 2 faces will remain because they point in the same y hat direction. And for the curved surface, we know that since dA and the electric field point in different directions, it will be 0 for the dot product. So we can view this as 2 separate integrals, one for the face on the left times dA y hat, negative dA y hat, and plus for the face on the right would be E y dotted with d a y hat. And so for both integrals, this would equal E times the area of the face, so plus E and then A. And so when we dot the y hats, they'll be 1. And so this integral will now equal E times 2A, will be the left-hand side of our equation for Gauss's law. And then we can have this just be equal to, this can be E or EY, but we'll note this is in the y hat direction since it's only the y hat component. And so focusing on the right-hand side of our of Gauss's law, we have Q enclosed over epsilon naught, but we need to know what this Q enclosed is. And to note, Q enclosed is equal to a volume integral of rho d tau. And so since this is a constant, you can pull it out of the volume integral d tau, and our volume integral will be of our Gaussian pillbox, which is a cylinder in this case. So for a cylinder, the volume is equal to the area of the faces on the left and right times the length of the cylinder, which we noted was 2y. And so putting this all together, we have on the left-hand side of the equation, we found was equal to 2EA, and the Q enclosed over epsilon naught is equal to rho times A times 2y, and equating these 2 things we are missing that, epsilon naught. So equating these 2 things, we have 2EA equals rho times A y epsilon naught. And so these 2 cancel out. And we note that we didn't need to know the area because the area cancels out for this equation. So E would simply be equal to rho times y over, and then times 1 over epsilon naught. And so this is for the y component, but like we said before, there is no x or z component in the electric field. So the electric field will be equal to 1 over epsilon naught times rho y in the y hat direction. And so this was the case for when our pillbox was within our slab, but we can extend this pillbox to be at a distance that is greater than the slab, so it's no longer contained within the slab. But we note some important things. So for this case, y is greater than d. So on the left-hand side of our equation, once again, our finding is this, but it will be equal to the exact same as we found above, because again, our areas of these circular surfaces has not changed, only our length has changed, and the electric field will still be pointing in the y hat direction. So we still have this on the left-hand side. But for the right-hand side, Q enclosed, no matter how far we stretch this pillbox to be, the charge only exists within the slab, so it must begin at D from negative D to D. And so we have a restriction there that no matter how far we extend this pillbox, it needs to the charge needs to begin from the infinite slab. So the volume integral will now equal same setup d tau, but the volume integral will now equal 2 d, the distance 2d times a. And so this is the important difference. Instead of 2y, we have 2d because our charge only exists within the slab, and the width of the slab is 2d. And we have the area of our circular surfaces of the pillbox. And so equating it, once again, we have 2EA equals rho times 2D times A. And our A's cancel out once again, 2's cancel out. And then, again, we are missing this epsilon naught. We have 1 over epsilon naught rho times d y hat direction, because it's still pointing in the y hat direction for this case. And so now our final part of the problem, we have to draw a graph of the electric field versus direction y. And so to make this a little clearer, we still have this y, but for here we can say EY component. And so some bounds here from D to negative D. And so from our first equation we have here, we note that this is a constant, our rho is a constant, and the only one that is variable is our y, and this is a linear equation. So we can say that this will have a positive linear slope. And so for here, it's just simply a line. And the equation of the line is 1 over epsilon naught rho y. But once we hit this boundary D, we have another equation that we just described right here. Same as before, the 1 over epsilon naught is a constant, rho is a constant, but D is now also a constant because it is this width of the infinite slab. So it'll be just a constant line that we are choosing to draw here. And so this can be extended down here. And once again, once it hits this negative D restriction, it'll be a constant line. And so here, this is the component for the electric field and the y component. So 1 E times D, that is the slope. And so just pointing it back, we have here our graphs. So this is the graph of the electric field plotted against the y direction. And so I hope you enjoyed this solution, and thank you for listening.